We're going to remind you about the fact that partial pressure tells us about gas in the atmosphere, particularly when we're talking about more than one gas, like oxygen and nitrogen in the atmosphere. But the partial pressure can also tell us about gas dissolved in a liquid. When we know that the gas in the gaseous state adjacent to the liquid comes into equilibrium with the gas dissolved in the liquid, then we can refer to the amount of gas dissolved in the liquid as being the same partial pressure as the gas in the atmosphere adjacent to it. So let's think about what happens in this champagne bottle. We've got the wine in there, and as it ferments, we have CO2 forming in it, and the CO2 is escaping into the atmosphere because we have very little CO2 in the atmosphere. So let's remind ourselves about that. P atmosphere, when we think about P CO2, it's essentially zero for all intent and purposes, very, very tiny. So any CO2 that forms in the liquid in the champagne will actually escape or trying to come in equilibrium with the gas above it, and it will just exit the bottle, and we'll have very little CO2 that will stay in the liquid form. But now we come along and we put a cork in this bottle like that. And then as the CO2 forms by the fermentation process in the liquid, in the champagne, and some of those, again, molecules are moving in different random directions, but some hit the surface and they form gas above the liquid, the pressure in here starts to go up. So I'm going to call this P bottle. The pressure will rise because gas is being formed within the wine and it is going into the gaseous state and it's just accumulating above the bottle. So the P bottle starts to go up, so that it's greater than P atmosphere. Now this will continue until we get into an equilibrium state where the partial pressure, again, is the same with respect to the amount of carbon dioxide that's in the gaseous state and the CO2 that's dissolved in the liquid or in equilibrium, and those partial pressures then are the same. And when that occurs, there's no more gas formation within the liquid, and we see a quiet liquid, no bubbles in it. That's what you see when you get that champagne bottle from the store. So now I have a P bottle that is greater, pressure in the bottle that's greater than pressure in the atmosphere, and it's time to drink the champagne, so we take the cork out, and we hear that pop sound. So we hear the pop because now we have equalization of pressure between what's in the bottle and the atmosphere. This is total pressure. We're not talking about partial pressures of gas now or anything. This is just that total pressure that had built up in the bottle by virtue of trapping the CO2 coming out of the wine. And when you get that equalization of pressure, that gives us a popping sound. Now, having removed the cork, the CO2 that had been accumulating above the liquid escapes, because there's no CO2 really in the atmosphere, so the CO2 will try to equilibrate throughout the atmosphere, and it escapes from that region above the liquid. But now suddenly I have a PCO2, a partial pressure of carbon dioxide above the liquid that's very low because there's very little CO2 in the atmosphere, and I've got a PCO2 in the liquid, again, that's the dissolved gas, that's very high. And so I'm in a disequilibrium with respect to partial pressure of CO2, and that means that the dissolved gas will suddenly come out of solution and form bubbles. And these bubbles will rise to the surface, the gas will be released from the bubble, and then will go out from the bottle. And these bubbles will continue to form until the partial pressure of CO2 dissolved in the liquid and in the atmosphere is basically the same, which is again almost zero. So that now explains why we have the pop with the cork, and it explains why when the cork comes out, and explains why the bubbles are not there initially but do appear once the cork has been removed. And all of this relates back to the notion of partial pressure as a representation of gas dissolved in a liquid and the interaction that undertakes with the gas above the liquid as well.